In the previous video, we talked about the cylindrical thin wall vessel. Now we're going to talk about spherical thin wall vessel. And in fact, spherical is actually easier than the cylindrical one. Why do I say so? I have a spherical sphere. If you look into this direction, the cross-sectional area is actually this one over here, right? Now it's this path over here, okay? And if you were to look into another dimension, by looking at this direction over here, you're gonna have a sectional area over here, the same thing, okay? And in fact, this cross-sectional is the same as this cross-sectional over here, alright? And if you were to look at the top, looking from the top, then you're gonna have a cross-sectional that is like this, right? So all these cross-sectional are all the same from where you see it. You see from here, you see from here, you see from anywhere. The cross-sectional is always the same. And what can we imply from here? We can straight away analyze things in terms of this one, alright? Where this is very similar to your sigma zz, alright? Where this one is all your so-called the sigma zz stress, you were to say, or whatever direction. You can be sigma zz, you can be sigma xx, because all the whole cylindrical system are all the same. You look from here, you look from here, they're all the same, and therefore this can be xx, yy, or zz. Anything that you want can be very happy, alright? And therefore in this case I still write as sigma zz, alright? And these are all the stresses that is acting along this particular surface, right? And this surface, this surface itself, it has a certain diameter, alright, or internal diameter, you would say. If you were to remember, if you want to derive a certain stress, because we are still going to derive a stress for this spherical system, so we're going to derive it. How do we derive it? Alright, we're going to still use summation of force is equals to 0, alright, because it's a static system. You just put it there and let it go. Let it go. Anyway, so we know force is actually sigma zz times the area, right? The 2 pi rt, alright, the internal diameter, because 2 pi r is actually your circumference multiplied by t times, alright, so times t of your circumference. So you have a certain circumference diameter over here, you to say, alright. So therefore in other words, this is just area lah. So this in terms of area, not diameter I'm talking. But anyway, yes, this is something that we have said earlier, right? And then this is the stress, alright, your longitudinal stress, if you were to say, alright. We also know that the pressure acts in 3 directions, right? Pressure acts in all these directions. So therefore, in this direction, we are talking about z direction. If we talk about this is x, this is y, this is z, then you're talking about the z direction. So sigma zz is coming over here, so it's a z direction, and therefore there will be a pressure that is acting against this thing, alright, acting along all this internal diameter stuff, alright, along this whole surface, as we say earlier, alright. And the reason we also don't know why, but we just take it as they are talking about the whole surfaces, and therefore it's minus the pressure itself times pi interior radius square. Alright, we're talking about that particular surface area that we are dealing with, all the pressure that is acting all along this thing, alright, within the spherical stuff. Alright, and therefore what we have is equals to, is over here is equals to 0, and then I'll just simply bring this over to the other side. What we have is this. So I didn't cheat your feeling. Now we're going to cancel out pi ri and pi ri, so all I have is just left with this one over here, alright. And now I can just simply re-represent this sigma zz as p r over 2t, or p ri over 2t, okay. Know that sigma zz can be represented in all directions. It can be xx, alright, xx, it can be yy, so all this can be represented with this equation in all directions, and therefore that's it, nothing much. Now something a bit blur comes in, alright. What blur is that? If you take a look in this cube over here, alright, if you take this cube, we will zoom it out, this thing, and just now we say that we are talking about the longitudinal system, sigma zz, alright? But what about the hoop stress, sigma theta theta? And what about the sigma rr, the radial stress? Alright, because it's thin wall, therefore the radial stress is actually in naught, because it's all about the pressure outside that's coming in now. It's not about the sigma r. It's actually negligible to a certain extent. This part we actually know, and this part I think you are clear, and therefore this is simply equals to 0. Okay, what about the hoop stress? Right, we can actually say that sigma zz is like this, then it goes all the way, and then we can measure our stuff, right, as we have mentioned earlier, as sigma zz. But what if we measure in terms of sigma theta theta? Alright, what is it all about that we have actually changed? Because if you measure in terms of sigma theta theta, if you remember back its equation, end of the day will be equals to PR over T. Alright, instead of our current equation of PR over 2T. Alright, why do we actually measure in terms of the longitudinal compared to the hoop stress? And the longitudinal stress should be like this. Okay, sorry. Yeah. So the longitudinal stress is something that we have measured just now. Alright, over here. But why don't we measure the hoop stress? We do say that we can actually know that it's a sphere, and therefore we measure in terms of the longitudinal stress. But also because it's a sphere, the hoop stress or in all directions can be also the same. Why don't we take the hoop stress? Why do we take the longitudinal stress? And this is something that raised my awareness. So let us take a look into how do we prove that it's actually PR over 2T for your hoop stress also. Actually, I take a slice of this sphere over here, alright, and this is the cube that we are talking about, the hoop stress going in this direction. Okay, now we're going to look into this direction because we are talking about hoop stress. We are going to look at the cross-sectional or the interior this portion over here. So if you look at it, you're going to look at it in this manner. So therefore, if you happen that if you look in this side, alright, it's something like this. Okay, and then if you look over here now, there's something over here. Right, so you will get something like this. Okay, this is your area over here, or your particular area. Alright, this is the T, and this is also a T. Alright, you're just sum of your thickness itself. Okay, and your hoop stress over here is simply going in this direction, sigma theta theta and sigma theta theta. Okay, now what's different from the longitudinal stress? For example, for the longitudinal, if you just take a look, alright, the longitudinal, sorry, in terms of the cylindrical one, alright, the cylindrical one, the hoop stress is something like this. If you were to look at this in this manner, alright, if you still remember, this is your little cube over here. Your hoop stress is all this area along this side, and therefore, if you're talking about dz, yeah, this times dz times t, alright, and therefore it is sigma theta theta dz times t, alright, for the cylindrical system. Okay, because it actually spans, alright, it's actually spanned in this longitudinal direction. So you're talking about the direction of dz. Alright, if you don't know what I mean, if you were to just take a look over here, alright, this is what I'm talking about, sigma theta theta times t dz, alright, which is talking about this thing over here. Alright, because you're looking in this direction, so you have some sort of a dz, alright, times t, some sort of it. Now, and there is actually two of the slices if you have to look in this direction, right? So this particular plane, if you remember, if it sparks a memory, you're looking at here. So this is t, this is t, alright? So therefore, there is 2 of this cube, and therefore we times 2, right, in the previous video. Now, for a spherical case, instead of a cylindrical one, which is going in this portion over here, if you want to talk about cylindrical, is this one, dz. Alright, we're gonna talk about it in terms of a cylindrical one. I mean in terms of a spherical one. Meaning is like this. So your cross-sectional Alright, instead of dz, alright, it's going. So when you look at this plane, you're gonna look at another circle, as we say just now, right? We're gonna look from any point. You're gonna look at it. You're just gonna look at a circle. Alright. So instead of looking at just this particular plane, which we have done earlier for the cylindrical one, we are talking about all this stuff over here. Alright, it's not just this two over here now. Alright, still doesn't look nice to you, or look so-called clearer to you. If you look in this direction, for sphere case you'll see another circle, or you're gonna see another ring over here. For cylindrical case, you're gonna just look at this lines over here, right? It's just this lines over here. If you were to look at just a dz with a thickness of t. Alright, but however, if you were to look in into this direction for spherical one, then this is t, correct? And this area itself, it's not just dz times t anymore. Alright, it's not just 2 times dz times t for a cylindrical one. You're going to talk about in terms of a circumference type of stuff, which is 2 pi r I t. Alright, this is due to this geometry type of stuff that we actually cause the hoop stress and the longitudinal stress to be the same. Alright, and this is a very clear defined understanding between the longitudinal one and the spherical one, because the longitudinal one talks about going in this direction, while this one is always the same. You look at any direction, is always a ring itself. Hope that this is somewhat of that clear intuition. If we do summation of force is equals to 0, then sigma theta theta, our hoop stress, alright, maybe will be multiplied with 2 pi r I t instead of previously in the cylindrical one is sigma theta theta times 2 dzt. Alright, because we are looking at this particular plane. Alright, this particular plane. Because we took an understanding of a certain dz only, a dz part. Alright, a little small portion and analyze, right? Therefore, if you have a hoop stress that is something like this over here, that is somewhat cylindrical in this direction, alright? So we are talking about actually in terms of the y direction, alright? If you were to just look at this part, so at first we look at this plane, and after that, look at this plane, we are actually looking at this particular point, we say, right? And then this is where we look at from this point of view, if you still remember. So if you were to look in this direction, you will see something like this. Or however, because it's a spherical one, you have something like this, right? If you can visualize, right, something like this, and therefore your so-called your sigma theta theta is going in this direction, right? It's going in this y direction, alright. And we actually solve for your sigma theta theta equation, the forces, right? This is your sigma stress, and this is your area that we have found earlier using what we have said, alright. And therefore, what is opposing this in terms of this pressure is all this stuff over here. Alright, all this stuff over here in the internal stuff, which is pressure times the pi r square. Alright, the internal pressure. So it's still in the y direction, right? We're now talking about that. And therefore, we'll just minus this equals to 0. And you will see something that is exactly the same. That it actually comes to this one. You will just take a look. This portion over here that we derived earlier from our longitudinal stress for the sphere is exactly the same if you were to derive from the point of view of a hoop stress. As you can see, 2 pi rt, 2 pi rt, PRIT, PRI square, sorry. The only thing is in terms of the stress ZZ and stress theta theta, and we know that stress ZZ and stress theta theta or wherever XYZ are all the same stuff. And therefore this is the whole proof of the spherical stuff. I mean spherical stress, which is sigma x or y or z is equals to PR over t, where this is the radius. I mean 2t, alright, 2 times thickness. Okay, so that's it. Next video.